enjoy your Friday at least a little bit. Okay, so machine learning, what is it? So we have to, we're on the 20th lecture of this course. 20th lecture, we're nearing the end, so we're getting into more advanced machine learning models. And so, what did we discuss last? Well, so the last two lectures were basically principal component analysis, k-means clustering, Gaussian mixture models. These are all examples of unsupervised learning. So today is yet another example of unsupervised learning, which is generative adversarial networks. So this is another example of unsupervised learning that we're going to discuss. And then, we're just going to slowly make our networks more complex. So beforehand, when we did classification, we had supervised learning, data, label, we want the model, predict the label, right? Then when we discuss PCA, when we discuss k-means clustering, we had data, we had a bunch of data, and we wanted to just use the data in some manner. So today we're gonna sort of piggyback off of that. And basically we're gonna piggyback off of that and do some more interesting things with unsupervised methods, building off PCA, building off k-means, building off all of that good stuff. So we're gonna get to know the theory behind generative adversarial networks. We're gonna go through implementation of GANs, and we're gonna go through the many uses of GANs. And particularly, I think, one of the things that I think makes this class unique compared to a lot of other things that you see online, with machine learning, I think there's a lot of people basically that will spit out the whole same, they'll spit out the same usage. They'll spit out the same party line of why things work, of sort of the concepts behind things. So we're going to go through that concept, but also I want to really spend some time on the implementation, because I feel like, at least for me personally, I only learn from examples. So hopefully that could be useful for you guys too. So yeah, unsupervised learning. So the two unsupervised learning tests that we discussed heavily. No. That's a weird error. That shouldn't happen with Markdown. Okay. So the three main supervised learning tasks that we discussed: clustering, data visualization we discussed, and compression. Compression, you guys will have a homework problem on compression in homework 9 coming up tomorrow. So clustering, basically segmenting data into groups without actually having labels. That's pretty important. PCA, we did that through just analyzing the feature space, finding eigenvalues, etc. With data visualization, again, that's mostly for us. That's mostly for us because we need a way to just sort of visualize the data space. We need a way to visualize the whole data set. And the data set has 784 dimensions. We are ultimately 3-dimensional, maybe 4-dimensional beings, depending on how you look at it. So we can't really visualize 1,000 dimensions. So what do? We need to compress the data. We need to organize it into a smaller number of dimensions. So that's another use of unsupervised learning. And then we have compression. We basically, again, we have the MNIST data set, 784 features or 784 pixels. Each pixel is a feature. Do we need that many features to represent some handwritten digits? No, not really. So you're going to see that in the homework, but that's basically the idea behind compression, that you could compress a lot of data into a smaller space, and then you could uncompress it and get the most of the data, most of it back, most of the qualities of it back. You don't lose very much information, okay? So the unsupervised task we haven't talked about yet is generation. And arguably, that is the biggest thing that's the biggest thing we use machine learning models for, or one of the biggest, I should say, depending on your field. So ChatGPT, like Gemini, all these things, these are generative models. They produce data, they produce new data that they haven't seen. So, you could take a This is from ChatGPT, by the way. I should write that down. Should write that somewhere. But you could take an image, for instance, the front of the ECE building. You could give it a prompt. The prompt was, make this into the style of Starry Night. And then ChatGPT will sort of recreate that image in the image of Starry Night. And it's actually quite beautiful. It does things pretty well, although all these wires only have a single wire going into the wire nut, making you wonder why the hell you would use a wire nut at all. So there are little things that logically make no sense, but you know, it's pretty to look at. So that's an example of generation, right? We create a new piece of data. We want that new piece of data to have the same characteristics as the other data set that we are getting inspired from. So in this case, the other data set we're getting inspired from is Starry Night. That piece, that famous painting. We want the new piece of data to be very close to that. Okay? But the thing is, we don't have an image of ECEB with Starry Night there. So what do? The machine has to sort of learn to generate a new piece of data. And the question is, how do we train that? How do we teach a model to create a new piece of data that has never been revealed before? Right? That's not supervised learning, because in supervised learning, I mean, the only way to do that in supervised learning would be basically to have all the images in the style of Starry Night and then send it through a model. I mean, we can't do that. There's way more prompts, and there's, you know, undecidable amount of problems, and, you know, a decidable amount, or decidable amount of problems and an undecidable amount of input space. I don't know. So we can't really train this in a classic supervised fashion. So the question is, how do we train a generative model? And so generative models come in many varieties. A generative model, the whole class of general models is, we basically call it implicit general models, which basically define a probability distribution. So you start off by sampling a fixed sample distribution. This is a code vector. And then the generator network uses that code vector and computes a differential function that maps the code vector to a piece of data in your data set. Okay, that's the idea. So you basically, the whole thing here is that you have, let me go to here. Remember Andre, oh man, what was his last name? Karpathy. I was going to say Kaspersky. Andre Karpathy's image of SciFar, here, right? This is what we looked at when we did PCA analysis, when we had a huge data set of images and we wanted to view it in a 2D space, right? So Andre's massive mural here is taking each of these images and pasting it in a 2D space according to its PCA reduction. Okay, a beautiful mural here. But think about what we're trying to do. We want to create a new image that hasn't been seen before, right? We want to create a new image. Now, this new image needs to have the same distribution as the images in your data set, as your images in your target data set. So this right here, this mural is a data distribution, right? It is a data distribution. It's basically saying images that are of marine life are sort of around there. Images that are of food, I guess, yeah. The images that are of food are around there. And images that aren't around here, these are not part of that data set, right? So even though this is compressed to 2D, even though an image has, let's say, 1,000 features, 100,000 features, depending on the resolution, we could represent that whole data set as a probability distribution. There are elements in that dimensions that belong to that data set, and then there are parts of that distribution, parts of that space that don't belong to that distribution. So what this generative model is trying to do is it's trying to recreate, oof, nope. There we go. What this generative model is trying to do is it's trying to recreate the distribution, the target distribution. So you have a target distribution, the true data distribution, and it's trying to just create images that, if you collect enough of them, it will give you the target distribution. Okay? It won't be perfect, but it wanted to be close enough. Okay? So what's the deal with the code vector? The deal with the code vector is, again, the network is deterministic. Okay? I mean, I'm going to say this with a small caveat, is that I'm sure if you search online, you could look at stochastic differential models and all of that. That's a whole different thing. But computing in general, in general is a deterministic process, right? So you have a model, and the model takes in some value, and it outputs something, right? So you want it to output an image here, and you want it to output an image, and you want it to output an image that adheres to this distribution. So what do? Well, you need to give it something in. And so in order to get it to output a variety of images, for instance, if we just want to output some random images that adhere to that distribution, we just input a bunch of random values, right? And then it sees a random value, and then it outputs that random image, right? This is the same idea of generating a random number. When you generate a random number, it doesn't come out of nowhere. It basically first gives the computer a seed. Then computer takes that seed, passes it through a whole mess of chaotic functions to get a random value at the output, right? And then that random value hopefully adheres to whatever distribution you want. It could be a normal distribution, a uniform distribution, whatever else, whatever. You could formulate a random generator to generate any distribution you want. Same thing here. Here, instead of generating random numbers, we're just right now we're just trying to generate random images. Okay, and we're trying to generate random images that adhere to a image distribution that we've seen before. Okay, does all that make sense? Okay, so again, yeah, so Andrej Karpathy's, I never get tired of looking at that, but again, the image here, I think this is SciFar. The image is here, so the image collection he has here, all these images here, these are all part of the distribution, and images outside of here are not part of it. So ideally, you want your network to generate images that are part of the distribution. You want it to generate images that would fall inside here, and you want it to not generate images that will fall outside here. So the idea is that the images that are inside here will be real images. Images that are outside of this distribution would probably represent nothing, would probably be static, right? Would probably be nothing visually interesting to us. Okay, so how many times? Okay, so that's what an implicit generative model does, okay? That's what an implicit generative model just generates a piece of data according to some distribution if given some random input. Okay. So the question is, how do we train such a network? So that is a big question, and there are multiple methods. Okay? Big thing that we need to remember, a big thing that we should know, you guys will just have to trust me on, is that if you try to do it directly, let's say, oh man, I was up very late last night. Let's say you want to do this directly. Let's say you're just going to randomly get a bunch of images. You're going to get just a huge network, a huge like CNN, like 50 convolutional layers. a bunch of linear layers, all that good activation functions. Just mix them, throw into activation functions, tanh, ReLU, leaky ReLU, sigmoid. Just throw all that in there. And then you take it, and then you put a bunch of random numbers in, and then train it, and then output and take the loss between an image in the data set and that random number. If you do that, I'm not going to lie to you, there is a possibility that it works, but it's very, very low possibility. It won't work well, okay? The direct training does not work well, and it's simply because usually you don't have enough images, okay? You just don't have enough images. You need a whole lot of images for that to work well, for basically a direct training method to work well. And it's because, there's no labels, there's no real feature space, so you're getting a bunch of random numbers. You're sort of mapping them to some images, which is fine. But the thing is, you're going to run out of images, so do you have to use the same random numbers for the same images? Do you have to do some random numbers correspond to certain images but not others? There's a whole bunch of weird nuances that the machine learning model will try to learn that you don't necessarily want it to learn, You give it a random number that's basically 1,015 and you map it to like a cat. Does that mean 1,015 corresponds to cats only? What if you take 1,016 and then you map it to a picture of a boat? So what will the model do then? It'll try to split that hair. Like say, 1,015 is definitely this picture of a cat. 1,016 is this picture of a boat, and it won't sort of generalize. Okay, and that's sort of the thing that we want with machine learning models. We want the ability to generalize. So direct training does not work well. And there's a bigger issue that, ideally we want images that we haven't seen before, right? The image right here of the ECB, we haven't seen this before. This has never existed before. And we want to know, does this make sense? If we get this from our model, is this a good image? How do we train it? Like, what should our loss function look like? Our model will spit out this, and then do we just compare it against the original Starry Night? That doesn't seem to make sense because there will be there definitely are significant differences. It's not clear how we adjust that loss function there, okay? So there's a bunch of issues there, okay? So direct training does not generalize well. And the larger issue is that we want a way to be able to say, we want to reward the model for generating a new image that looks like it could belong to the new data set. And we want a way to punish the model for generating an image that is way off, that is very, very obvious does not belong to the original image space, right? So what do we do in that case? Well, we need to discriminate between good images and bad images. So that is what we'll do. We need to build a model. We need to have our generative model. But instead of simply fixing the output to a particular image from the data set, instead what we'll do is train another model. So the other model takes in whatever the generator generates and discriminates and tries to guess, is this image a real image? i.e., did it come from an actual data set that we're interested in? Or did this image come from just something that was generated? Is this completely made up? So this architecture right here is what's called a discriminator. We have a generator. You get a new image from just some random input. We get a new image. Ideally, this new image will look like it belongs to the original data set. But in order to test whether or not this image belongs to the original data set, or it should look like it belongs to the original data set, we'll train another model. And this model's only job is sort of to say, All right, if I get this image, I'm supposed to say false, the picture is not real. If I get an image from the actual data set, I'm supposed to say true, it is real. Yeah, please tell me.
So when is this considered successful then? Because I guess they're going to be training each other. So when do you, like are we saying that the generator is good or the discriminator is good? Because, you know, if the discriminator is doing its job, the generator isn't. And if the generator is doing its job, the discriminator isn't.
Oh, perfect question. So how do we know if the models are doing good? Because the question was, as you astutely pointed out, if the generator is doing a really good job, then the discriminator will have a bad job, and it's going to start doing a poor job. If the generator is doing a bad job and the discriminator is really good, then the discriminator is going to be doing a really good job, but the generator is going to be doing a bad job. So you have this. So you have this battle between the two, right? So that's what makes this actually what's called. This is why we have the term adversarial in the name. You have these two models, and their objectives are in conflict, right? One model's objective is to fool its partner, and the other model's objective is to figure out when its partner is lying. So these are contradictory goals, right? So how do we formulate? So I will answer your question in the next couple of slides. How do we formulate how do we formulate when the models are doing good? So let's go on to that. So we formulate how well a model is doing by a loss function, same as anything else. It's always a loss function, okay? And this is where machine learning gets a little mathy, okay? There's a difference between mathematical models and mathy models. Mathematical models are something like very tangible, very absolute. You could comprehend the input and output. You could calculate it yourself. Mathy models are what happens when, something gets so complex that, yes, it does make sense, but the model is more a sort of a formalization of logic than something that you actually calculate, okay? So for instance, the models that the loss functions that we used in the beginning of the course, where we had basically some sample data sets, and then we could calculate the loss ourselves when we're trying to fit a function when we're trying to fit data to a very complex function. That was a mathematical model. Mathy models are basically, like you see in a lot of sort of sociology or economics papers or something. You have a model, this variable represents X, this variable represents the people that are in X, and then, they're related by the log of the inverse of the cosine of whatever, right? Is there a truth to it? I mean, when you look at the data, the model fits, but there's no fundamental truth to it, right? Same idea here. Right here, the loss functions now start going from something that were derived, for instance, binary cross-entropy loss, where we actually derive that out why that's important. The loss function now goes to something that we're just trying to formulate our logic, okay? And hopefully, thankfully, we live in a day and age where, where we have complex libraries that a whole bunch of engineers have spent decades worth of man-hours on to sort of take our formalized logic and make it into a mathematical model instead of a mathy model, okay? So what's our loss function look like in this case? Well, let's have some notation. Let's just put down some notation. Let's say that the generator, we'll denote the generator as G. It takes in, we denote the generator as G. It takes in some random code vector Z. So this is just some random value, and it has some parameters theta, right? Okay, so this generator outputs a particular piece of data. It's an n-dimensional data. For instance, if we wanted it to output the mnist character, then we will have it output then it's going to output, a vector or a 28 by 28 vector of 784 values between 0 and 1, right? And then we have our discriminant model. We'll denote that as D. It has parameters W. And our discriminator model outputs 1 if the image is real. Okay? If the image is part of the original data set X, then it's supposed to output 1. And if it's not part of if it doesn't believe the image is part of the data set X, it outputs a 0. And then if it has a whole continuous space between 0 and 1 that determines its confidence that an image is real. Okay? So it outputs anything between 0 and 1, denoted corresponding to if the image is 0. So for our discriminator, the loss function for our discriminator should be if it gets a image, if it gets a real image, X, okay? X is a real image. Actually, maybe I should write that. X is a image from the target data set. Okay? If it gets a real image, then we pass it through the discriminator. And the discriminator will output either something 0, or I mean, if it gets a real image, we want it to output a 1, right? So if it outputs a 1, then the log of 1 will be 0. And so that is the bottom of our loss, 0, right? If it outputs anything less than 1, if it outputs 0.9 and our image is real, then that means our log of that would be something greater than 1. It will be negative something greater than 1, right? And then negative times a negative will be positive. So it will be something greater, something greater than 0. So sorry, something greater than 0. So if the discriminator outputs something less than 1 for a real image, it will be something negative. It will be negative some value. And then negative times the negative, that's where this negative comes from. Negative some value will give you that value. And so you would have something greater than 0 for the loss. Okay? So this is our loss function if the image is real. If the image is fake, let's say we will have a particular random, we have those random inputs into the generator. Okay? Again, those random inputs, it's literally, let's say a vector of 100 values of just random numbers, okay? So if our image is fake, then what do? We want it to output a 0, right? We want it to output a 0. So instead of saying this directly, we can't just do log of this value directly because it will give you undefined if it outputs a 0, a complete 0. We just simply say we want it to, if DW outputs a 0 when the image is fake, then we want the loss to be 0. So instead, we take the loss of 1 minus the confidence that the discriminator estimates it's fake. So if it estimates anything greater than 0, then this whole thing becomes less than 1. Then you have some negative, some value. The negatives cancel out, and you get some positive value in the loss function. Does that make sense? I know I'm playing with negatives a lot. I'm playing with negatives a lot, but the important thing to note is that with the loss, we're just using the properties of log to say that we basically want always to get, the ideal case is if we get a log of 1. So we want the discriminator, we want this function inside the log to output 1 if it's correct. So if the discriminator gets a real image, it's correct. It should output a 1, and then it will be correct. If the discriminator gets a fake image, it should output a 0. So you just take 1 minus the discriminator, and then it will be correct in that way. Okay? Everyone good with that? Okay, so that's how that loss works. On the other hand, the loss function, the cost function for the generator is reverse, right? We want it to fool the discriminator. So what do we want? We want it to fool the discriminator, i.e. we want the discriminator to estimate a 1 when the image is fake, and yeah, we want it to estimate a 1 when the image is fake, right? So what do we do in that case? Well, this stuff, we have G, and then G has a bunch of parameters theta. So really, if we take the derivative of G, these will end up not mattering anyway. So we don't need to worry about this part of the function. Instead, we need to worry about this part of the function, okay? Because the only place theta is present is right there, okay? So if we look at the loss function here, we see that if we want to optimize the generator, we want to optimize the parameters of the generator, such that we can, I know what I did. Oh, I know what I did. Okay, never mind. Okay, so we want to optimize the generator so that this here becomes as large as possible. So before, right here, we would try to minimize the discriminator loss function, right? Over here, we want to maximize the generator loss function, right? Because we want, basically, the discriminator to estimate that whatever this generator gives is real. We want it to give a 1, and then if we give it a 1, the closer it gets to 1, the closer log gets to 0, and then the more this whole expression explodes. Okay? So what we want to do, we want to minimize the discriminator loss, and we want to maximize the generator loss. Okay? So this actually occurs many times in machine learning, most famously in GANs, but it does appear in other models. But this is very, very well known as a mini-max formulation. Okay? Basically, you have a particular loss function where you're trying to minimize some aspects of your architecture. You're trying to modify parts of your architecture so it minimizes that loss function, and then you're trying to change other parts of your architecture, other parameters, so it maximizes the loss function, right? So you have a loss function that looks at your entire architecture. The GAN is really 2 parts, 2 models put together. A discriminator which has a bunch of parameters W, and a generator which has a bunch of parameters theta. Yep, a generator which has a bunch of parameters theta. And so using this same loss function, we want to minimize the loss function. We want to modify W to minimize this loss function, but at the same time, we want to modify theta to maximize this loss function. So you have that sort of dichotomy going on. Okay? So this is a formulation for what you were saying, Dominique, that you have 2 different desires. The generator wants to screw over the discriminator because it wants the discriminator to perform badly. It wants it to basically be fooled. And the discriminator wants to keep the generator honest. It wants it to work hard to produce something that even we would be convinced belongs to the data set if we didn't know better. Yeah, please, Daniel. D omega, where's omega?
Sorry, DW.
Oh, DW, oh yeah, oh yeah, omega, sorry. yeah, DW is 0, 1.
From 0 to 1, then log 1 minus DW, GC to D would be from 0 to 1 as well, right?
Would be log 1 minus DW would be, yeah, from 0 to 1 as well, yeah.
So if DW goes to 1, then log will go to positive within, right?
If DW goes to 1, well, it's going to 1 from 0, right?
So it's going to positive within. Or is it going to negative?
Am I getting my logs mixed up? Hold on. Log 0.5. I think that it has to be negative, right? Yeah, it gives you a negative value, right? If anything below 1, it gives you a negative value. The log function gives you a negative value. Anything above 1, the log function gives you a positive value.
So when DW goes to 1, log will go to
So when dw, so when this goes to 1, when the discriminator goes to 1 here, this gives you, this whole thing gives you a negative value. And then that times the negative here gives you a positive value. Yeah. 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 I know, you're playing with negatives a lot, so it's easy to get confused. Yeah. Yeah. Yeah, and exactly. So remember that we're keeping things the same. We're trying to keep the loss function the same because it's going to be really annoying if we have to have two different loss functions. So we try and keep the loss function the same. So we could keep the loss function the same, but we want to minimize this. We want to minimize the loss function here. We want to change the parameters w to minimize this loss function, but we want to change the parameters theta to maximize this loss function. Okay. Yeah. Yeah. Okay. So all that makes sense? Yep. Okay. So this is the basic formulation. This is like version 0 of the loss function for a GAN. Okay. Now there is a problem here. There is a problem here, which is why it didn't, like, the GANs sort of only became popular, like, not only became popular, but really came to popularity in 2014-ish with the seminal paper that's referenced in the end of the slides. And there is a issue here, which is that where you want to maximize theta, minimize w, so that this whole thing, we want to minimize w to minimize this whole thing, and then we want to change theta to maximize this whole thing, right? But let's ignore this part. Let's ignore this part for a moment. This is the center part, and look at simply maximizing theta if we want maximizing this function with respect to theta. Okay. So let's say the generator is really, really good. At some point in our training process, the generator is just astounding. It's generating images that will make, it's generating images, it's generating images that are very close to the original data set. So the original, so it generates, so the discriminator is unable to, the discriminator will simply output a 1. It will approach a 1 because the generator has become so good. Okay? So what happens in this case? This case, the total expression is very large. This whole thing becomes very, this whole thing becomes very large, which is what we want, right? Great. But what if the reverse is true? What if the discriminator is really, really good, but the generator is really, really bad? Okay? I mean, what if it's always able to tell that what an image from the generator is? So the loss function will be very, very close to 0, right? This whole thing will be very close to 0, which is okay. Which is okay. I mean, we want the discriminator to be good, so the loss function, it will be very close to 0. But when we try to optimize theta, when we try to optimize the parameters theta, right? When we take this derivative, like the massive derivative, we're going to have a massive have like a massive network, and we're going to take the derivative with respect to, we're going to take the derivative of the loss and then modify the parameters of theta. What will happen when this whole thing is close to 0? Well, the derivative will be close to 0, and then the change in parameters will be very close to 0, right? So this has happened to us once before, right? Does anyone remember when this issue has come up before? Yeah, please. Yeah, Ben.
Was it when we were discussing the sigmoid function with steps, it would get too small, the steps wouldn't be able to move along the sigmoid?
Yep, exactly. When we were discussing the sigmoid function, we came into this issue again, that if the model was very confidently wrong, right? If the model was very confidently wrong in some extreme, we wanted to change the parameters, and we should change the parameters greatly, but the sigmoid function at the extremes is basically flat, right? And because it's basically flat, the gradient would also be close to 0. And so we have a problem there. So it means that training the parameters for the generator would become an issue there, right? So how do we fix that problem? Well, I should note before I forget, this is called the saturation problem, basically for obvious reasons. You saturate your sort of confidence. You become very, very confident in a wrong direction, and then it simply completely kills the gradients. So how do we fix the saturation problem? We fix it basically the same way we fix the sigmoid function. We do it by simply changing that. We do it by simply reformulating the loss function. And in this case, we reformulate it by changing that max into a min. Okay? So when we change the max into a min, we're saying we want to change sort of the direction of the growth of this whole function. So instead of doing 1 minus dwg0z, we are instead just going to say log of dw g theta z. Okay, so what will happen here? Well, if the discriminator is really good, but the generator is really bad, then this will mean that the discriminator will give you a 0, will give you something close to 0, and this will give you something close to 0, which would make the log of this value, the negative log of this value very large. And so you want to minimize that. So this will make it very large, and you want to minimize that so you would have a very effective gradient that way. Okay? So you readjust this term, you put it back here, and that is how you get your loss function for general adversarial networks. And it basically mirrors what you get with binary cross-entropy loss. That is binary cross-entropy loss, right? Taking that into account, taking into account the label. Remember, binary cross-entropy loss, we derived it by simply doing the label. We simply took into account the actual labels. We were like y times log plus 1 minus y times log, that whole thing. Same idea here. Same idea here. So we just change around this min theta, this max theta to a min theta, and we change around this function so that everything works more copacetically. Okay? So what's special here is that because we change this around, it plays much more nicely with PyTorch, right? It plays much more nicely with PyTorch because all the loss functions that PyTorch gives us by default, they want us, all the optimizers PyTorch gives us, the assumption is we want to minimize values. All right, so if we get binary cross-entropy loss, if we use binary cross-entropy loss with this, we want to minimize it, so that's why we have to have the minimization term there also. Okay, everything works out. Cool, so that's the logic behind GANs, or that's the logic behind training GANs, optimizer. Or that's the logic behind optimizing generative adversarial networks. We'll talk a little bit more about how to train them. But let's do that through an example. Okay? So let's talk about an example. Specifically, let's talk about our favorite sort of favorite motivating data set, which is MNIST. And, oh, nope, that's 8. Really? Only 6? Oh, Lord. There. Let's make screen bigger. Okay. So what do we want to do? Let's say we want to generate fake images that look like they belong in the MNIST data set. So remember, the MNIST data set is simply a collection of handwritten numerical digits. Okay. There are 10 possibilities. This is a labeled data set, but we're going to ignore the labels. And we just want to, create a generator network that just creates handwritten digits, right? Okay, so how do we do that? Well, same thing we do. We have a generator. The generator takes in some control vector. That's just a random noise. It generates a fake image. This fake image is given to the discriminator where it determines real or fake. We also give it some real images where the discriminator has to test whether something is real or fake. Okay? So how do we write this in code? Well, it's not too bad. We simply need to have two models. Okay? We need to have two models. One is a generator. And for the generator, I'm just keeping this simple. Really, what I should be doing is using convolutional neural network, convolutional layers, and all of that. These are images, so probably convolutionals will work better. But you know, I'm being lazy, so I just put in a bunch of linear layers. The data set is simple enough where you probably don't need. I mean, you don't really need convolutional layers. So I just put in a bunch of linear layers. Just basically went from a. We go from some particular input. The input has some latent dimension. I think I set the input dimension to 100, and we just pass it through a linear layer to get the dimension count to 128. Then we expand, get the dimension count to 256. We fan out the layer, get it to 512. Then we eventually take the big layer and then create a 28 by 28 image. Okay, so very simple linear network that we've seen 100 times before. Yep, simple network we've seen 100 times before. Then we have a discriminator network, and the discriminator network is similarly simple. We have just 3 different linear layers. We take in a particular image, 28 by 28 image. Then we pass it through to a linear layer. That's 512. Then we take that and reduce it down to 256 features. Then we reduce it down from 256 features all the way down to one single feature. And then we pass this feature to the sigmoid function, right? Because the output of the discriminator is a single value, either 1 if the discriminator believes that the image is real, or a 0 if the discriminator believes that the image is fake. Yeah, Dominic.
Is there a reason you're using, like, you use ReLU, hyperbolic tangent, leaky ReLU, and sigmoid? Or is there a reason you're switching between all of them?
Oh, is there a reason for these different activation functions? Not really. Just sort of instinctually, I know what will probably work best, so I just put that in. But it will probably work. I mean, I'm sure. Actually, I don't know exactly. You could test it, but I'm pretty sure that even if you replace this leaky ReLU with normal ReLU, it'll work fine. You could use sigmoid instead of tanh. Wait, could you use sigmoid instead of tanh? Yes, yeah, you could use sigmoid instead of tanh in that case. It would just change sort of the image. Actually, I probably should have used sigmoid instead of tanh now that I'm thinking about it. Yes, I definitely should have. Because I think I normalized my image to be between 0 and 1. And the issue is that tanh is between -1 and 1. So I probably shouldn't have done that. That's a good catch. Anyway, but yeah, there's no specific reason. You just sort of try a bunch of stuff, and then something will eventually work. And if it works well, great. Well is a relative term. Something will work, then you just mess with the parameters, get it work a little better, and then the paper deadline's coming up, so then you're like, well, this is it. I'm just gonna put the code into a zip file, write the paper, and be done with it. Good. Thank you. I'm gonna try that at least the next time around. Next time around, I'm gonna test to see if that works better. But again, discriminator takes in an image, outputs a single value. Generator takes in something. It takes in a vector it takes in a random vector, and it outputs a image, a 28 by 28 image. Or in this case, a flattened 28 by 28 image, because MNIST is so simple. Okay, so does that, okay, so let me go through, actually, I don't need to. Let me get out of the slide mode. There we go. Oh. Oh, okay, there we go. Um, so hyperparameter, so the latent dimension is indeed 100, batch size 64. Remember what batches do? You basically combine the gradients of a bunch of different images together, because training becomes more stable in that case. You don't want that constant like random noise. So if you have batches, training becomes much more stable. Number of epochs, you could choose any number. In this case, well, actually, the results I have are for, I think, an epoch of 160 or something, just because I was short on time. But I think epochs of 300 or so works best in this case. But you'll still need a substantially, you'll need a GPU, and it'll be like an hour or two training. Anyway, it's not a super optimized GAN network, but it's just sort of a very bare bones one. So we want to get a model, a generator instance, discriminator instance. We want to use an optimizer for the generator. I guess I mean, in past, I've given you guys sample code with stochastic gradient descent, which would work for probably also here. But in general, in practice, the atom optimizer is pretty standard. It just people have found that it works better than others. And then the parameters here correspond to different parameters for the advanced optimization functions. Like, we talked about momentum and stuff. That's what this is for. So play around with these values. The learning rate is really, really low, just to make the training slightly more stable. Again, play around with the learning rate. And then the loss would simply be the binary cross-entropy loss, right? Because we reformulated we fixed the saturation issue before, and so when we fixed the saturation issue before, it basically became very similar to it basically became equivalent to the cross-entropy loss we have seen 100 times before. Okay. All right. So data, as far as data set goes, we could just load the data sets directly. We can load the MNIST data set directly, and yeah, and the rest of this is just for visualization. Okay, so we have the discriminator, we have the generator model. Now the question is, how do we train them? Right? Do we train them all at once? Do we train them one at a time? So how do we train these things? Is the question, and in order to do that, come on back here. There we go. So how we train this is actually pretty simple. We first train the discriminator. We first make sure the discriminator is optimized. Then we train the generator. Okay. Linking them together would yield unideal results. So training them separately should work fine right now, because in order to train the discriminator, we need to get a bunch of random images from the generator, and then to estimate fake or true, and then we need to get a bunch of random images from the actual data set in order for it to guess real, right? With the generator, we want the discriminator to stay standard, right? We want the discriminator to basically know that we want the discriminator to estimate that the model is saying, we want the discriminator to, we don't want the discriminator to change while the generator is trying to generate a new image, right? Because if the discriminator is changing while the generator is trying to generate more realistic images, it just yields instability, right? The generator would have to hit sort of a moving target, which makes training the generator much more difficult. So in this case, we'll keep the discriminator values constant, and instead we give the generator, we just generate some random samples, we pass it to the discriminator, and we just use the loss function to determine whatever values of the generator should change. Okay? So for each, so we're training both the models separately, okay? Because the discriminator needs to get data from the generator in order to be trained. So we can't have the generator changing and the data, the input data for the discriminator changing while this is being trained. It becomes unstable. Same thing in reverse for the generator. Okay. So how does this translate to code? Well, very, very simply. Actually, let me go back. Yep. How does this translate into code? It's basically, we take the training loop. For each of the training loop, we calculate we have a vector. So for the batch sizes, we have a vector of, yes, this is real, labels that this is a real image, and then we have labels for, that we have sort of the ideal outputs for the discriminator if the images are fake. So we either have ones, a vector of ones, or a vector of zeros. That vector corresponds to the batch, okay? It's a vector because we have a batch. If there was no batch, if we were doing this one image at a time, it would simply be a single one and it will be a single zero, okay? So what do we do? First thing we need to do is train the generator, which is, well, we could do it reverse too, but we could first train the generator, which is simply that we zero out the gradient of the generator. We generate a bunch of random inputs. We generate a bunch of images from those random inputs, and we put each of those images into the discriminator, and we basically set the discriminator to be, true. Yeah, we put those images into the discriminator. Yep, there we go. We put those images into the discriminator. We calculate the loss between the true value and the we want the discriminator to output a 1, but the discriminator hopefully is good enough to not output a 1. It will probably be fooled by at least some of the images, so it will output a 0 or whatever. We calculate the loss between those values, and we calculate the gradient, and then we optimize the generator. Does that make sense? So the target so I want to just emphasize this. The target when we're training the generator is that the discriminator outputs true, right? That's the target. Now, if the generator isn't working optimally, then it will probably the discriminator will probably be good enough to output a 0, right? But that's not the target. We want it, but if it outputs a 0, the difference between 0 and 1, that will be the loss, and then you will propagate the loss back into the generator network, and then you would optimize the generator network. Does that make sense? Okay. Same thing with the discriminator, or slightly similar. We zero out the gradient of the discriminator. We calculate the loss. We first feed the discriminator real images, and then we tell the discriminator, you're supposed to output 1s for those real images, because these are real images. You're supposed to output a 1. And then if it doesn't output a 1, there's a loss, and then we have a loss there. For the fake images, similarly, we capture a bunch of generated images. And then, kind of important, is to detach these images, because you don't want the gradient to propagate into the generator. Okay? You don't want to train the generator at this step. So if you separate the images, then the gradient would not propagate into the generator parameters. Okay? Kind of important. So we simply get a bunch of generated images, we pass that into the discriminator, and we tell the discriminator, you're supposed to output a 0 with these images. And then if it doesn't output the 0, there will be a loss. And then you get that sort of fake loss. You average these two losses together simply because you have the same number of real images and the fake images. So you could average these two losses together. You back propagate, and then you optimize. Okay? So first you train the generator. Then you train the discriminator. And then you do a bunch of bookkeeping. You calculate the epoch loss. You do calculate the images at each epoch, and so on and so forth, okay? So for every 25 epochs, I mean, right here it's just formulated, so at every 20-ish epochs, I captured some sample images from the generator so we could view what it's looking, okay? So what do we start off with? This is after This is after 20 epochs, actually. And we see that after 20 epochs, that the generator already starts outputting some images that sort of look like digits, but also not completely, right? It's rough. I forgot to capture the at epoch 0. At epoch 0, it basically outputs just noise. So at epoch 0 outputs noise. At epoch 20, it starts getting something. And then you see after 100, 150 epochs, it starts outputting some images that could definitely be mistaken for actual MNIST data points. You see? MNIST images. So you see it's getting better and better every time. So this is after 150 epochs. If you run this for the full 300, you'll get some very strong results that you could put into the actual data set. Okay? And then if you look at the loss, one important thing, if you look at the loss, we want to look at the loss and see what does the loss represent. So let's ignore the generator loss for a moment. Let's look at the discriminator loss. What is this discriminator loss? Why is it hovering around 50? Why does it sort of plateau around 50? Any ideas? Yeah, Ben, please.
As you train the model, the generator gets better, and so the discriminator is guessing essentially becomes random.
Yeah, yeah. Yeah, that's exactly it. We want basically, because Azure is an adversarial network, so if the generator gets too good, then the discriminator will have to get better. But if the discriminator gets too good, then the generated images have to get better. So always you'll sort of, you'll sort of end up with a discriminator that hovers around 50%. It guesses some of the inputs, it guesses some of the fake images correctly, and it guesses some of the fake images incorrectly. Okay, and that's really what you want. And so it gets progressively more difficult to estimate the fake and real images. And in fact, the generator loss doesn't mean a whole lot. But what we see is that even though the loss here stays relatively stable, we see that the generator actually gets far, far better at generating actual data points that belong to the data set. Okay? And actually, one thing that's cool about the MNIST is that, especially with the earlier data points, you see it getting very good at you see it constantly generating ones and stuff, like simple shapes, 1s and 4s. And then after a while, you see it generating more complex shapes, like 9s and 2s and stuff, because those shapes are more difficult to, I don't know why, but I guess those shapes are more difficult to generate, so that those shapes only come up later in the training process. Yeah, it's hard to actually measure. It's hard to actually measure when these shapes come up, because then you would have to have a classification network and all of that. But actually, that might be an interesting project. That might be an interesting demo. Maybe I'll do that next time. Yeah, Downey.
Is there any benefit to the discriminator being wrong, like one way more than the other, like saying what the generated image wasn't when it really was, or like is like pretty much like p-miss versus p false alarm?
Is there a benefit for the discriminator to be wrong?
I mean, wrong, like is it better for the discriminator to be wrong about the thing being real than it being fake?
I don't know. That seems like an open problem. I mean, in general, you don't want the discriminator to be too good or too bad. You know, you sort of want to hover around that 50% part, because on one hand, if it's too good, then then even though we fix the sort of loss function, it still sort of affects the generator. During the early generator training, it does make it harder for the generator to get even slightly good at generating images, right? So if the discriminator starts off perfect, and then if the discriminator starts off perfect and the generator starts off basically at random, it'll be very hard for the generator to get to an actual image, even with like a large loss, because you're fighting against. It's like putting up a 5-year-old against like an NBA player at a basketball match. Like, I mean, it would be a learning lesson for the 5-year-old, but it probably won't contribute much for his skill. It should just be dominated by someone, right? But it's much better if he has someone at equivalent skill that they slowly make each other better, and eventually he works up to the NBA player, right? So I don't know if there's a benefit if the discriminator is better one way or the other. But if you find a paper, let me know. That's an interesting question. Yeah, please. Yeah.
So just to clarify, right now we're not giving any consideration to the labels on the images, right? We're just taking the data
Yep.
as a whole.
Yep, right now we're not even considering the labels. We're just taking the data set as a whole. And then if you want labels, we could talk about how to manage that in a moment. But again, like just for here, data sets, yep, data set, data loader, torch utils, where's the images? Images, yep, there we go. Yep, there we go, here we go. So from the data loader, we're taking the images and then we're basically tossing the labels. Yeah. So all we're trying to do is represent the MNIST thing, the MNIST data set. And then if we wanted to, for instance, represent sort of the MNIST 5's data set and stuff, we could do that also. It would just be slightly different. We would just have to, instead of the code vector being a random thing, we could add in a label, like a one-hot label to the code vector, and then have it say, you want to generate a 5 when this label is supposed to be a 5. And then at the same time, for the discriminator, we would have to give it images of 5s. And so it would get better at developing images of 5s when the label is 5. Right? And we'll talk about that more in a minute. So,
I guess each label can kind of just be treated as a separate problem then?
yeah, exactly. It becomes basically, you just treat it as a separate problem. Okay. And how do you treat things as a separate problem in machine learning? You just add a slightly more dimensions to the input space, and then hopefully the model figures it out. Okay. Yeah. Yeah, so, okay, before you go, so a couple things I wanted to mention. Well, okay, I'm gonna make this very quick. So, in the code, you'll notice I try to avoid GPU training as much as possible, but as the models are getting more and more complex, running them on a CPU isn't really useful. So I wanted to just toss in a bit about GPU training because you guys are probably gonna start your projects and you might need it. So you could use Google Colab or Kaggle or something to give you GPU models, they give you GPU instances. And all you really need to do for training your code on a GPU is simply first find if you have a GPU available to you. So Torch gives you this nice .device function that tells you if you have a GPU available to you. Then you simply move the models to the GPU. Then you move the data. Then you move the datas to the GPU. And everything else is the same. Okay? So literally, it couldn't be simpler. You just have to move the data. You have to move the models to the GPU. And everything works much faster. And I highly recommend making sure you have a GPU at your disposal because training these larger models becomes very, very slow and tedious without them. Also, so just to finish off our talks about GANs, GANs have developed greatly since 2014. 2014 was a seminal paper basically titled Generative Adversarial Networks that sort of made GANs very popular. Since then, this is a 2017 paper where they use GANs to create high-resolution images. So not just celebrity faces, but the celebrity faces is important because really in order to recognize faces, you need this thing to be high resolution. And the way they train, if you just try to train the GAN right from the start, it becomes very difficult. Like just flat out do it the way I did. Basically define a model and just train it that way. It'll take forever and probably not yield very good results. This paper actually found that one way to improve the training of the GAN is simply to start off with a very small model that gives you a very rough image, train that, and then make the model slightly bigger and have it give you a slightly greater resolution image. Train that, make it slightly bigger, give it have it train a slightly bigger resolution image, train that, and so on and so on. So basically you're going from a small model giving a crappy image, but still, like, you know, related. You get a small model, crappy image, to larger and larger and larger models to higher resolution image. So this is actually a very common, this is a very common technique you see in a lot of different machine learning networks now, but this is especially important in GANs in order to get some visually pleasing data. CycleGAN was also a big thing. Basically, that you wanted to, there is this thing called style transfer in machine learning. And we saw it basically in the beginning of the slide. I wanted to paint the outside of the ECEB building in the image of Starry Night. So doing that, the term for that is style transfer. And really, there's multiple different ways to do this, diffusion models and stuff. But one way that works exceptionally well with GANs is simply the same idea that we just were discussing. We give the GAN a particular input image. We have it give a real image in the style that we desire. And then we discriminate between the real image in the style that we desire and the changed image, and that the generator changed that to that style. Okay? And the clever thing here is that not only do we want the generator to be able to change the image to the new style, we also want another generator to change the generated image back to the original image. Why is that? Because if you don't have this step, basically the generator is just going to generate any random image. It'll just sort of treat this as a random vector. It'll treat this as a random input and just generate a random image in the same style. Random image of zebras. But because you have this second generator network that you want to retrieve the original image from, you can't treat this as a random image. The random image, information from the random image has to stay contained in the generated image. So you basically get the style you get that style applied to the input image. Okay? So that was a very clever idea. This was called CycleGAN, reference in there. You could check out the loss function there. Other things, one other thing. So sort of combining those two ideas was a big paper, StackGAN, basically a GAN model, but again, we learned that StackGAN, but basically the idea here is we want to go from a text description to an image. So basically what ChatGPT does, effectively, right? So how do we do that? Well, we put the text image, we give it to the generator, and then we take the text image, generate a sample from the text image. We discriminate between that sample and the input image, and then we output a 1 or a 0. And then this combines the other iterative training process that we saw earlier, because first we generate sort of a rough image that's 64 by 64, a very low resolution image, then discriminate based off that. Then we train a larger generator to get a higher resolution image and a larger discriminator to better discriminate between the generated and real images and discriminate based off that. So you have multiple stages of generation and discrimination. And doing that, same idea, you could go from a text segment to an actual image. Okay? So that's largely that's the basic idea behind how a lot of these large language models work. This is one of the many, many ways that they train large language models. Okay, so many different uses. There's a nice little GitHub repository of many different actual coding examples of GANs. If you want to check it out, that's a link to that. And that's all for today. And so homework 9 will be posted either by tomorrow or by Saturday. There's one problem that we're still working through. The project descriptions have been posted. Kaggle infrastructure is coming shortly. Again, one topic, we just need to finalize that contest. And most importantly, have a good weekend. All right, guys.